Welcome back, Physics 30. The next few videos we'll look at section 26.4 and kind of the consequences of special relativity. In particular, look at time dilation and the twin paradox. And you watched a video before this discussion, so hopefully you're aware of how that works. And there's also a couple of videos after you'll look at as well. So the fact that two events simultaneous to one observer may not be simultaneous to a second observer suggests that time itself is not absolute. So we looked at that in the last video here, in that it depends on what reference frame you're talking about, especially going at high speeds. This is indeed just what Einstein's theory of relativity predicts, as the following experiment shows. So on the next page we'll see figure 26 shows a spaceship traveling past Earth at high speed. The point of view of an observer on the spaceship is shown in the first part, and that of an observer on Earth in part B. Both observers have accurate clocks, they're synchronized. The person on the spaceship flashes a light and measures the time it takes the light to travel directly across the spaceship and return after reflecting from a mirror. And in the reference frame of the spaceship, the light to travel that distance is d, so to go there and back, it'd obviously be 2d. And so the time to travel back there and back is this. So here, if we look at to look at the speed equation, distance over time, and we could rearrange it to find this. And so someone on the spaceship would just simply see the light go back and forth against the mirror, but to someone on Earth watching the spaceship fly by, as you saw in the little video I have here before this, it takes an angular path, because as the ship is traveling away from you, you see the light go in this angled path, which is a larger distance. Now the textbook here goes through the derivation of this particular formula right here relatively quickly and skips a lot of steps. So what I've done is I've written down kind of every step to show exactly how in the heck this equation got derived in this few steps. Okay, so if you grab a piece of loose leaf, you may want to copy this out. Looking at the two different points of view, so if we have the observer in the ship, so as illustrated in the previous diagram, there the distance separating these two light clock mirrors is d, and of course to go there and back, that'd be a distance of d plus d, which is 2d. So if you just look at a regular speed equation, change in distance over change in time, in our particular case the thing that's traveling is light, so we'll use the speed of light, 3.00 times 10 to the 8 meters per second. We'll just call it c. Of course the distance traveled there and back is d plus d, or just 2d, and we'll just simply specify the time the same way the textbook did, delta t naught, a little zero down here indicating the time, and we'll use that symbol to represent the time experienced on the ship by someone on the ship or in the ship. Okay, so all I did here, I just rearranged this to solve for t, or just bring the t to the same side, because you'll see that's going to come into play later. So multiplied each side by delta t naught, and we get this. So this is what the time experienced by someone on the ship would be. Okay, so that's relatively easy. Now, the observer on Earth watching what's going on the ship. Okay, so V is equal to d over t. Now this is the interesting part. So the light clock, so here just there and back. Now this is really, there wouldn't be any angle here, just be there and back, but to illustrate it with the arrows here, there's a slight angle here, but of course it wouldn't be. Just someone on the ship. As far as he or she is concerned, it's just there and back. But watching the ship speed away at a relatively high speed, the bottom mirror, by the time it's moved, it has to hit the top mirror, and then hits the bottom mirror again. So as you can see, it forms two right triangles here, and here, where L and L represents the distance that the ship has traveled in the time that that light was witnessed. So if this is L, and if this is D, A squared plus B squared equals C squared, or L squared plus D squared equals this part squared. So right down here, using the Pythagorean theorem, I just simply substituted in d squared plus L squared equals, I'll just call it C squared. And it's, of course, to solve for C, it's the square root of d squared plus L squared. Now this isn't the speed of light, I just used the old theorem how it usually is stated, a squared plus b squared equals c squared. So this represents this length, that the path that the light travels. This represents the path that the light travels on the other side. So that is our d over there. Square root of this plus square root of this gives us 2 square root of d squared plus l squared. And t, I'll just leave it as delta t, but still distinguishing it from the t that's on the ship. Okay, so this is the time observed by someone outside of the ship. Okay, and again here, what I did here is I just multiplied each side by t, because again this will come into play later. Just bring the t over to this side. And also, what was done in the textbook is looking at, okay, let's substitute this L value. And of course, L represents the distance that the ship is going, because the ship is moving at a relatively fast speed, so it's covering a certain distance in a certain time. Of course, the time that's being covered here is the time for this to happen when it's moving this horizontal distance. So looking over here, v equals distance over time, but in our case it's L and L. In that time period it takes light to travel that extended path. So v is equal to 2L over delta t, multiplied each side by t, multiplied by t, I get t times v equals 2L, and then lastly divide by 2, and there I get a relationship for L, representing it in terms of the time that passed by from observer on Earth, seeing what's happening inside the ship, and also the speed at which the ship is traveling. So we have that, and don't forget this L inside the radical sign here is squared, so I'll be squaring this TV over 2. So t squared, v squared, and the 2 on the denominator is squared to give us 4. Okay, so we have that so far. So we have a certain time period on the ship experienced by someone on the ship. Then we have a time period experienced by someone off the ship on Earth watching the event happen, and the expression looks something like that. Okay, with that, now as you can see, they skipped a lot of steps in the textbook here. I'm going to show you all the steps here to see how we did it. Okay, so what can be done next here is obviously we're going to try to get rid of that radical sign here. So if we square both sides, c squared t squared, 2 squared is 4, and then this underneath the radical sign, when we square a radical, it just simply drops the radical sign. You can replace it with brackets, just like saying the square root of 2 times the square root of 2 is just 2. The square root of all of this is just simply that value left over. Then distribute the 4 across, so 4 times d squared is 4d squared. 4 times this part here, you can see the 4's are going to cancel out, and we're left with t squared v squared. Okay. Eventually rearranging this and solving for t. So you can see here, I'll just bring the t's to the left hand side, minus t squared v squared minus t squared v squared. And I get this on the left with 4d squared on the right. Again, I'm solving for t, so in math class you would have seen 2 terms here with the common factor of t. We can factor out t squared. So t squared times c squared gives us this part, minus t squared times v squared gives us this part. Okay, and then solve for t squared, of course. It's t squared multiplied by all of this section, so if I divide each side by c squared v minus v squared, here and here, cancels out, I get t squared is equal to this part. And of course solve for t, that means taking the square root of each side, and I get this. So we have the square root of 4d squared is just simply 2d. The bottom part here will be square rooted. And then I'm going to substitute for the 2d part from an earlier part. You saw that I started earlier on. That's going to come into play. We're going to have to look at that in the next video because I'm running out of time here. Okay, we'll see you shortly.